Okay, guys, we're going to look at, in this video, we're going to look at vectors and some of the basic components of vectors and basic things that we can do with vectors and how vectors can kind of model real-world scenarios in a pretty basic way. So let's take a look. First of all, vector is just a geometric representation of a quantity. So it's actually an amount, and it has two independent properties. The first independent property that a vector has is a magnitude. Okay, so a magnitude is simply a measure of quantity. It's a measure of how much. Okay, so the first thing that we're looking at with vectors is how much. It represents a quantity or a force. A vector does. So the first thing that we want to know about that force is how much force do we actually have. The second thing, well, but actually before we move on, the way that we deal with quantity or magnitude is we actually represent this with length. And I'll show you how this works in a second. But the nice thing about vectors is that a lot of the things that we've done with regard to triangles and those types of things geometrically, we can actually just use length to figure out this particular property of vectors. So if we can go and find length, then we can actually figure out how much force is being applied. The second thing that we want to know with respect to vectors is not only how much force is being applied, but in which direction. So where is that force being applied? And when we talk about direction, we're really talking about an angle as it relates to our XY plane. So here with magnitude, we're talking about how much force is being applied. Down here, we're talking about where, or the angle at which that force is being applied. All right, so to put this into context, here's a little bit of a scenario. A man pushes an object forward with 5 pounds of force. At the same time, a second person pushes the object to the right with 2 pounds of force. Construct a diagram modeling this scenario. So first and foremost, here's my object. And most of the time, we just model these objects with squares, and then we draw a point right in the middle, which we call the center of mass. Okay. So secondly, what we want to do is for each one of these forces, we want to know how much force, because that's relevant. This one is applying more force than this one is, but we also want to know in which direction these forces are being applied. And so a vector looks like this. It basically looks like an arrow, and we're going to draw it from the center of that mass. Okay. So if I use this vector to represent 5 pounds of force, this guy pushes this object forward, so we just model forward with like up in this particular scenario. At the same time, a second person pushes the object to the right with 2 pounds of force. Okay, so if this represents 5 pounds of force, what we do is we use length to represent the amount of force that's being applied. And so I would draw this as a shorter vector relative to the first one. All right, so this is our 2 pound force that's being applied to the right. And so I think intuitively when we connect, or when we take this concept, someone's pushing something forward or up in this particular case, another person is pushing it to the right. We know that ultimately when these two combine, we're going to get something that looks like up and to the right. So to us, it kind of makes sense that that's going to be the ultimate result, or what we call the net force. So the way that we model this is called the tip-to-tail method. This is the geometric way that we model it. And essentially what we're going to do is we're going to take the first vector, and on the tip of the first vector, we're going to put the tail of the second vector. So basically we just kind of combine these two. And what results is something that essentially just gives us an overall composite result of these two forces acting together. So we'll get into more of the technical stuff as we go along, but that hopefully gives us a good general overview of how we can use vectors, first of all, to model both direction and magnitude, and also how we can combine vectors to get an overall net force. Okay, so the next thing that we want to take a look at are just kind of some little technical things that have to do with vectors. So because vectors are quantities that have direction, we have to make sure that we distinguish between the starting points and the ending points. And what I mean by that is that this vector, this is, first of all, notationally, the way that we write this is vector PQ is written like this. Okay, so vector PQ starts at point P, and you can see the arrow extends to point Q, meaning that this is called the initial point. So we're starting here at 2, 5. It extends all the way to Q, which we call the terminal point. Terminal point. Okay, so what I want to make note of is that this vector PQ is a very different vector than, let me get this flipped here real quick, up and down, and hopefully now you can see vector QP. Now vector QP has the same exact points, but vector QP starts at point Q and ends at point P. So we've got, essentially, if we're comparing these two things, we know that these vectors have both length and direction. So if we look and compare these two vectors, we notice that vector QP has the same exact length, but the direction is completely opposite. And so we need to make sure that we distinguish between those two things. So these would have the same length but different direction. So we got to be careful about calling these things the same vectors. They're definitely not the same vector. We distinguish that by the way that we write those notationally, and also by the initial point and the terminal point. So just to finish up this thought, same length and different direction. All right, so let's check this out real quick. So vectors have both magnitude and direction. It doesn't necessarily matter where they are located on the XY plane, though. And so because it doesn't necessarily matter where they're located, and what I mean by that is this vector in particular has a starting point at 2, 0, and an initial point at 2, 0, and a terminal point at 4, 12. Well, as far as we're concerned, all we're really worried about is how much did this change in the x direction, this particular vector, and how much did it change in the y direction? Because from that, we can determine both our magnitude and direction. So change in the x direction is essentially, here's my starting point, here's my ending point, how far did I go left and right? So in this case, I went from 2 over to 4, so I changed 2 in the x direction. In the y direction, I went from 0 all the way up to 12 from my initial point to my terminal point, so I went 12 in the y direction. And so if I'm going to write this as what we call a position vector, we would say that PQ, vector PQ, is equal to, we changed 2 in the x direction, and we changed 12 in the y direction. And so for any vector, this is typically the way that we write these vectors. We write them as position vectors. We also write these, another way to say this is write them in component form. Write this vector in component form, because what this tells me is what is the x component, or in other words, how have we changed in the x direction? And that component, this first component of this position vector, is going to tell me how we changed in the x direction. And the second component, here 12, is going to tell me how do we change in the y direction. So we have this component form, or in other words, a position vector is going to tell us we went to right and up 12. Okay, so for AB over here, I'm sorry, BA, and again, make sure that we pay attention to how we wrote these things, how we write these vectors. BA, vector BA can be written, well, that tells us we went from B, so we went from -1 to -10, so we traveled -9 in the x direction, and from 11 to 5, we went -6 in the y direction. So we have this component form, or this unit vector, that we use to represent these vectors. And so to go back up to the first point, it doesn't necessarily matter where these vectors are located on the xy plane. So I can take this vector PQ and I can move it around this graph, and the location of the initial point and the terminal point would change, but more importantly, what we're worried about is magnitude and direction. And so you can see that I can move this thing around and my length is not going to change, and also my direction is not going to change. You know, this thing is still pointed up and to the right, a little bit further up than it is to the right. And so I can use this position vector, or use this vector in component form in order to represent that I've gone right 2 and up 12. And same thing over here. I can move this thing around the graph, and it doesn't really matter the location. I can still use this form right here, this position vector, to represent the magnitude and the direction, or to find the magnitude and the direction of that thing. All right, so that's the next question, is how do we find the magnitude and direction of a vector? And really this comes down to, when we start talking about magnitude, remember we can use length to represent magnitude, or the amount of force. So if we can use length, essentially what I need to do is find how long this line is, or this vector is. And this comes directly from these component forms. So if I go ahead and model, I can drop an altitude down and create this right triangle, and that's essentially what these are representing. So this is the amount in the x direction, this is the amount in the y direction. I know that I can find the magnitude of vector PQ, and here's a little bit of notation for you. Magnitude of vector PQ looks like this. It's kind of like double absolute value type things. But I can find the magnitude of vector PQ simply by using Pythagorean theorem. Okay, so if I want to find the length of the hypotenuse here, I'm going to go ahead and take the square root of 2 squared plus 12 squared. Go through and simplify that. This is 144 plus 4, so that's 148. So that equals the square root of 148. And typically when we're talking about magnitude, we want to go ahead and find an exact value for that. So plug it into your calculator, and you should get the square root of 148 is about 12.17. And that's in units. So this would be my magnitude. When we're trying to figure out direction, and this is very important that you understand this, direction is directly related to, if we start this on this horizontal line, okay? So we always start, when we're finding direction, on this horizontal axis right here, and we're going to rotate counterclockwise until we hit our vector. So I'm going to take this thing, rotate it counterclockwise until I hit my vector. And this is the number of degrees that we have to rotate until we hit that thing is going to be our direction. And so for this particular case, I'm interested, again, this is a right triangle, I'm interested in finding this angle down here. So that's theta, and I can use my trig function. So my direction of vector PQ can be found using trig functions, and theta is going to allow me to find that. So here I've got my opposite is 12. My adjacent is 2, so I can use the inverse tangent function, or the arctangent of 12 over 2 in order to find that angle, and go through and solve. And you'll find that that angle is 80.54 degrees. So this would be the direction. All right, so the last part of this, just do one more example of finding the magnitude and direction of a vector. So this one a little bit different vector. It's got a component form, or position vector of -9, -6. And we're going to position that here on the origin. And what we're trying to figure out first is the magnitude. So if I'm going to find the magnitude, we're going to create this triangle. Again, the magnitude of BA, we denote this with these with this symbol here. So we've got magnitude of vector BA looks like that. So magnitude of vector BA is equal to, so what we have to figure out is, what does this triangle look like? Well, we know we go down 6. So that has a side length of 6. This one we went left 9. So for us, again, it's a length. So we're only interested in the positive lengths. Okay. So if I want to find this, I know that's my hypotenuse. So I'm going to take the square root of 6 squared plus 9 squared using Pythagorean theorem. That ends up being 36 and 81. And simplifying, taking the square root of that, we get about 10.82. So there's my magnitude. I want to find my direction, and this is where you really have to pay attention. So we followed the same rule as we did before, and that rule stated basically we're going to start on this axis right here. So when we start on this axis, we rotate around until we hit our vector. Well, that's going to indicate what our direction is. So basically what we're going to do is we're going to use this reference angle right here. We can find this reference angle and then relate that back to the direction of this particular vector. All right, so I've got my triangle. It's got a side of 6, a side of 9 there, and theta is the angle measure that I'm trying to find. So I know I can find theta by using that inverse tangent function. And the opposite is 6, adjacent is 9, so 6 over 9 are 2/3. Plug that into my calculator, I get theta equals 33.7, about 33.7 degrees. All right, so what we have to be careful of is that's not necessarily our direction. Our direction is how far do we have to travel in the counterclockwise direction in order to hit our vector. And so taking us to the horizontal line right here is going to give us 180. So the way that we find this direction is we take our 180 and we add this reference angle right here that we just found, which is 33.7, and that will give us the direction of what there was this BA. So that ends up giving us about 213.7. That's the direction of our vector, and we're good to go.